Sharon is building a rectangular play area for her baby. One side will be against the house, and the other 3 sides will be made of fencing. If she has 24 feet of fencing available, what are the dimensions of the play area with the largest possible area? All right, we're going to need a diagram for this, so let's make our house first. So I know this is a long, skinny house, but it'll do. I don't want to take up too much space. So that is the house. In fact, we'll write house here just to show. I hope you're amused. And then she's making a rectangular play area. And one side is against the house, but the other 3 sides are made of fencing. So we've got this play area. We can call this the area. And those 3 sides are made of fencing. And we are told she has 24 feet of fencing available. What are the dimensions of the play area with the largest possible area? Now, we could call the sides of this x and y if we wanted to. The other side would then also be x. And we could say that the area is x times y. But the problem is we don't know multivariable calculus yet. We can't deal with functions of 2 variables. So what we need to do is we need to write everything in terms of x. Now there's a piece of information we haven't used yet here. That piece of information is that Sharon has 24 feet of fencing available. So if we add the sides together, which are 2x plus y, at least the sides made of fencing, we know that the total is equal to 24 feet. And so we can actually solve for y in terms of x here. If we subtract 2x from both sides, this gives us y equals 24 minus 2x. And so we can replace this side, instead of calling it y, we can call that length 24 minus 2x. And now we can have the area just as a function of x. We know the area is base times height, or length times width. This is going to be x times 24 minus 2x. And we could leave it like that, or we could distribute the x and write this as 24x minus 2x squared. Either way, this is the area as a function of x. And now that we have this, we have a continuous function that we want to find the maximum value of. We also need a closed interval, but we can come up with that because we only have 24 feet of fencing. So the least x could be was 0, because if x is 0, then it's just flat 24 feet of fencing against the house, which is a little bit ridiculous, but it is possible. So x is greater than or equal to 0. And as far as the maximum x could be, if x was 12 feet, then our fence would go out 12 feet and then come back 12 feet, and it would have no width, but it would be fencing, and that would use up all of the fence. So the largest x can be is 12. So this gives us our closed interval, and this gives us our continuous function that we want to find the maximum of. So we can use the closed interval method. We're going to need the derivative of our area. So this is going to be a prime of x. And the derivative of 24x is just 24, minus the derivative of 2x squared is 4x. This is never undefined, so we just need to know when it equals 0. And that's not difficult. If we add 4x to both sides and divide by 4, we get x equals 6. So x equals 6 is a critical number. And then also we have to look at the endpoints. X equals 0 and x equals 12, the endpoints of those intervals. We have to evaluate the area at these numbers. Now, if x is 6, then the area is 24 times 6, which is 144, minus 2 times 6 squared. 6 squared is 36, times 2 is 72, and 144 minus 72 is 72. So that's going to be 72, and this is going to be square feet. Now, if we plug in 0 for x, of course the area is going to be 0. And the same is going to be true if we plug in 12 for x. 24 times 12 is 288. And then 2 times 12 squared is also 288. 288 minus 288 is 0. But also, we can plug in 12 here, right? These are just two different ways to write the area function. And if we plug in 12 here, 2 times 12 is 24, and 24 minus 24 is 0. So either way, these give us 0. And of course that makes sense, because the first one was what happened if we just took the 24 feet of fencing and placed it directly against the house. And the other one was if we did a weird out and back by placing the fencing out 12 feet and back. Both of those have no area because they're not real rectangles. They're just line segments. And so the only actual answer here that makes sense is 72 square feet. That is the maximum area. We weren't actually asked what the maximum area is. We're asked what are the dimensions of the play area with the largest area. So we know that x equals 6 gives us our one side. So that's going to be 6. And then 24 minus 2 times 6. 24 minus 12 is 12. So the dimensions are 6 feet by 12 feet. So the dimensions are 6 feet by 12 feet. And we weren't asked for the area, but we might as well say, giving us 72 square feet of area. And that's that. This one was a little different from the previous few examples, all of which gave us the function directly. This one we actually had to figure out what the function was going to be ourselves using a little bit of geometry and some logic. And if you're in my class, you will see a little bit later in this unit, we're going to come back to optimization problems, and we're going to focus more on these more advanced examples where we have to use a bit of geometry and some other things to figure out what the formula or the equation is going to be. So right now the focus is on the ones where we give you the equation, makes life easy, but we want to get our toes wet so that later we're ready to come back and look at the more advanced examples.